So we need to calculate diamagnetic susceptibility. So how we will calculate? Suppose an electron is revolving with radius r, so current will be charged per unit time E by T, and the time period omega is 2 pi by T, so T can be written as 2 pi by omega. So the magnetic moment for this is current into area E by T into pi r square. With calculation we will putting the value of T as this, we get the expression m equals to E omega r square by 2, and here one new term is there, me. What is me? This is a rest mass of electron. What is this rest mass? Relative to an observer when the speed is 0, it is the relative rest mass of an electron. Now the angular momentum, what it will be? I into omega. This is angular velocity. I is what? Moment of inertia for the electron who is moving in this. So moment of inertia for the revolving electron, that is m into r square into omega. So our angular momentum expression is me omega r square, and magnetic moment expression is this. So from this two expression, when we divide, or we are not dividing here in this case, now this is a normal case scenario. Now when it is put in a magnetic field, we will see these two cases where the magnetic Lorentz force and the centripetal force are in the opposite direction, and in this case, as you can see, Lorentz force and centripetal force both are in the same direction. So the Lorentz force, what is Lorentz force? QV into B, learned from electrostat. So I mean magnetostatics. The Lorentz equation is EV into B. In general, it is for both. So in general, what will be the case? It will be Fe plus Fm, that is centripetal force, and Lorentz force will be equals to the angular momentum, that is me omega r square. See, this is me omega r square for the normal condition. This is me omega dash whole square r. This dash is because of the magnetic field which we have applied now. So after the magnetic field applied, this is the case, Fe plus minus Fm by me omega dash square r at equilibrium. This is the condition. I have given the names. This is the new angular velocity. Now the centripetal force, it is given as me r square omega, that is same as the angular momentum as we see. Okay, and the Lorentz force EV into B. V is the angular velocity, so it can be replaced as r omega dash. So Fe plus Fm equals to this. Fe value we got, Fm value we got. We put this equals to this. Now when we equate, when we calculate it further, taking commons, we get at the final E omega dash B equals to me 2 omega dash del omega. Omega dash 2 omega dash is this, and to have taken as same. So omega dash plus omega is 2 omega dash. This difference I have written as del omega. So our expression is this. So from this we can write del omega, this goes to this side, okay, del omega, this goes below this, del omega equals to EB by 2me. This is called the Larmor's frequency. Okay, now from this equation 1, what we got from here is this magnetic moment. We are just rearranging it a little more. Del m equals to me omega r square. We are just taking the del values, so it will come something like this. This del omega, I have put this value. Okay, this omega become del omega, and this del omega become this. So from this I got the magnetic moment. It was in the normal condition, and now when the field is applied, this is the moment. Now here, as you can see, this r, when the field is applied, this r can be replaced by something called sigma. What is this sigma? It is nothing but the projection of r perpendicular to the magnetic field. Okay, so we just replaced r square by sigma. So del m equals to minus e square b. In place of r square, we got sigma square by 4me. So this r in the three axes is the summation of x square plus z square plus y square. but this sigma square, since it is the projection of r square, it will be the same. But here see, z is not there. Why z is not there? Because z is along the applied field. So for r this 3 axes, and for sigma only 2 axes. So for r we got 3x square. X symmetry, both 3 axes will be equal, x, y, z. So 3x square, and sigma is this 2, x square is same as y square, this, so 2x square. Sigma square equals to 2/3 r square. Summing it up, we divided it by z. What is z? This is the atomic number of atom. Now the contribution, now this all this what we did, the contribution of it towards the magnetic moment from an atom I mean. So contribution towards magnetic moment from an single atom is this, minus e square bz by 4m into 2/3 r square. I did nothing, I just put this sigma value. Okay, sigma value I just put in that equation. So for n atom it is this, for single atom, and for n number of atoms it will be induced magnetic moment per unit volume. Okay, so what is our susceptibility? M by h. M value we have got this, divided by h, we got diamagnetic susceptibility. A bit lengthy, but it's easy.